Hello, everyone. It's a great pleasure for me to report the research Jiagu, which targets on optimizing resource utilization for serverless computing. This work is finished by Qingyuan Liu, Yanning Yang, Dong Du, and other mates from iPads Lab, Huawei Cloud, and EPFL, and I'm Jiao Chen. First, let's talk about the background and motivation. Serverless is the popular cloud paradigm where users only need to upload their code, while platforms are responsible for DevOps. Serverless systems have three key components. First is the scheduler. When a new instance is created, the scheduler would choose a node to deploy it. Different scheduling policies are used for different scheduling targets. Once instances are deployed and initialized, when users send requests to a function, a router or gateway is responsible to distribute the request to a specific instance. Here, RPS, that is request per second, is used to measure the user load. Function 1 here has the load of 20 RPS. In a serverless system, a function handles requests with multiple homogeneous instances, where the user load fluctuates. Serverless systems would automatically scale instances with an autoscaler. A common autoscaling policy is to use RPS to calculate the required number of instances. For example, function 1's saturated load is 20 RPS. When the RPS rises from 20 to 30, each instance is overloaded. Then autoscaler would calculate that the function needs 2 instances and created a new one. The instance would then be scheduled and deployed to a node. After the new function 1's instance is deployed, according to the load balancing policy, the router would equally distribute requests to the 2 instances, thus avoiding overloading. On the other hand, when the RPS drops, for example, from 30 to 10, each instance is underloaded, processing only 5 RPS. When autoscaler finds that 1 instance is enough, so it chooses an instance to evict it, thus saving resources. Okay, so nowadays, an important issue of serverless systems is that the resource utilization is low. Resources are seriously wasted and underutilized. In Huawei Cloud, 90% of nodes have less than 10% of CPU utilization. How to efficiently utilize resources and saving costs is the mostly concerned issues for most organizations. Every 1% increase in resource utilization would mean billions of dollars in savings. So, to improve resource utilization, we would focus on 2 root causes. One is the resource over-provisioning. Another is the load overestimation. I will talk about them one by one, about how the wastage is caused and the challenges of the prior works to mitigate the wastage. First, let's talk about the resource over-provisioning. We know that each instance is configured resources mainly because the instance needs to meet its performance requirements, that is, its QoS requirements. For example, a function's QoS could be that its 99% tail latency should be less than 20 seconds. However, even if the instances are processing the same load, their performance vary, and their resource requirements differ in different situations. For example, when the instance in the fig is processing a full load, that is an RPC of 20, the function 1 instance in case 1 may need only 1.2 cores to process 20 RPS and guarantee QoS. However, in case 2, function 1 is interfered by its neighbors, which results in degradation of performance, so it may need 2 cores to process 20 RPS and guarantee QoS. Therefore, since the instance is required to handle saturated load of requests and guarantee QoS under various interference scenarios, the user will conservatively allocate more resource to the instance. For example, in this case, the instance requires at least 2 cores of resources to satisfy both case 1 and case 2. This makes the resource wasted in some cases. For example, in case 1, the instance wastes 0.8 cores. Therefore, the over-provisioning of saturated instances caused the first part of resource wastage. As shown in the picture, when the interference changes, the requirement of instance resources also changes. If resources are allocated conservatively according to the highest resource requirements, then this part of the fig in white is wasted. Okay, so here comes the second part of resource wastage. The second part is caused by unpredictable load fluctuation. The user load in the cloud is always fluctuating. So the resource requirement of users also fluctuates accordingly. The actual resource requirement is, of course, lower than the requirement when processing the saturated load. If we conservatively assume that the load is always saturated, it would mean that load overestimation and resource wastage. For example, in this picture, when the IPS drops from 20 to 15, the resource requirement drops from 1.2 to 0.9. If we always allocate resources assuming the saturated load, it would cause resource wastage of 0.3 cores. Therefore, for the second part, the overestimation of resource requirements caused by load fluctuation further contributes to the low resource utilization. Many prior works try to mitigate the 2 parts of wastage. However, they face the challenges of the trade-off between high effectiveness and low cost. Let's talk about the challenges for mitigating the 2 parts one by one. To mitigate the first part, overcommitment can be helpful. In this example, the node has 3 cores, while an instance requires 2. So as usual, only 1 instance can be deployed. However, when scheduling, the scheduler can predict that whether co-locating 2 instances can guarantee QoS. If so, like in the example, an instance only requires 1.2 cores to guarantee QoS after co-location, so the scheduler can deploy them on 1 node, thus increasing the deployment density and the resource utilization. Therefore, the key of overcommitment is that the scheduler should accurately predict QoS violations after the deployment density is deliberately increased. Otherwise, the user experience could be influenced. To predict instance QoS after overcommitment, many prior works leverage various models. However, the challenge is that the prediction cannot achieve high accuracy and low cost simultaneously. Some works use complex models, considering many features and could make accurate prediction. However, it could cost tens or even hundreds of milliseconds. Such overhead could contribute to the cold start latency. Since the cold start is optimized to milliseconds or even sub-milliseconds by prior works, the costly prediction could become the new bottleneck. Other works make predictions using simple heuristic models or historical information, which could make fast prediction, but cannot make accurate predictions due to the overly simplified models or require unscalable profiling costs. To mitigate the second part, autoscaler can be helpful. For example, when the load drops, the autoscaler would invoke an instance after keep alive duration, thus mitigating the resource wastage caused by resource underloading. Obviously, if the autoscaler is more sensitive, the idle resources could be reutilized soon after load drops, which means higher resource utilization. However, more sensitive autoscaling also means more cold starts. If we will evict instances in time when load drops, then we need to recreate those instances if the load rises. It brings additional cold starts. Therefore, for the autoscaler, it is challenging to achieve high utilization and the low cold starts costs simultaneously. In a nutshell, overcommitment and autoscaler both have trade-offs between high effectiveness and low costs. Faced with these challenges, Jiagu uses tool design to break those trade-offs, achieving high effectiveness and low costs simultaneously for both overcommitment and autoscaling. Let's talk about them one by one. First is the design to solve the challenge of overcommitment. Recall that for overcommitment, when the scaler is choosing a node for a new instance, it needs to predict whether the QoS can be guaranteed after deploying the instance on that chosen node. Since after overcommitment, the deployment density is deliberately increased. Therefore, the costly prediction is on the critical path of scheduling. This is the root cause of the trade-off between prediction accuracy and cost. So, if we could assume that how instances come before the instance actually arrive, for example, assume that an instance of function 1 will come to node 1. By doing so, we actually assume the future co-location scenario on node 1. That is, the new instance of function 1 is co-located with current instances on node 1. So we can predict the performance according to the assumed co-location scenario in advance. Then, when scheduling a newly incoming instance, for example, if the new arriving instance happens to be the instance of function 1, it means the actual co-location scenario matches the assumption of prediction. We can directly make decisions with the prediction results. No need to make on-path predictions. Therefore, we can remove the costly predictions from the critical path. It looks great, but there are an infinite number of scenarios of possible incoming instances. We cannot traverse all possible collocation environments. To solve that challenge, we found that serverless highly replicated nature could help. According to Huawei traces, we found that most instances are highly replicated. It means that if an instance belongs to function 1, then there could also be many other instances of function 1. According to our statistics, 56% of instances are of functions that have more than 12 replicated instances. If an instance of function 1 is already deployed, it is likely that there will be the second, the third, the fourth instance of function 1 arriving in the future. According to the characteristic, to predict future co-location scenarios, we can make predictions for the next instances of existing functions on a node, predict whether their next incoming instances can be deployed. Specifically, we can construct a capacity table for every node with advanced predictions. Every entry in the table means that the maximum QoS guaranteed concurrency of the functions on that node. For example, node 1 has deployed 2 function 1 and 1 function 2 instances. Function 1's capacity is 8, means that at most 8 function 1's instances can be co-located and guarantee QoS with current neighbors. That is 1 function 2's instance. Function 2's capacity is 1, meaning that only 1 function 2's instance can be co-located with 2 function 1's instances. Then, after we constructed the capacity table, when function 1 arrives, the scheduler wants to know whether function 1 can be deployed to the node. It could directly check the capacity table. The table says that one more function 1 would not surpass its capacity. So the scheduling can be done directly without making on-path predictions. This is the fast path of scheduling. Similarly, if arriving instance is function 2, the scheduler also knows that one more function 2 could mean the number of instances surpassing its capacity. which means QoS violation after deployment. So it would deny this scheduling and choose another node. It is also the fast pass. Then, if function 3 comes, since the capacity table has no entry for function 3, the scheduler needs to make predictions when scheduling, calculating the capacity of function 3 and make scheduling decisions accordingly. Since this time, we need to update the capacity table when scheduling, which incurs additional prediction costs to the scheduling critical path. It is the scheduling slow path, with which the scheduling performance is similar to the prior works. Although the slow path still exists, the highly replicated nature of serverless workload makes sure that the number of slow paths is much less than the number of fast paths. According to the analysis on real-world traces, scheduling with fast path tasks takes about 90% of total schedulings. Capacity table is calculated based on current co-location environments, which requires timely updates since the co-location environment is constantly changing. Jiagu introduces a synchronous update to keep the capacity table up to date and prevent the updating from introducing prediction overhead in the critical path. More details can be found in the paper. For how to calculate the capacity value and some examples, also more details can be found in the paper. Now, we introduce how Jiagu tackled the challenge for autoscaling, achieving high utilization without additional cold starts. The insight is that the autoscaler allocates and releases resource by instance creation and eviction. This coupling is the root cause of the additional cold starts. Therefore, we need to decouple these parts to achieving both high utilization and low cold starts overhead. Therefore, we introduce dual-stage scaling. Assume that at the first second, the load drops. Prior autoscaling methods evict instances directly after a keep alive duration. Instead, we add a new phase before evicting instances, called releasing phase. In this phase, the router changes the distribution of requests, letting only 2 instances process requests. The 2 instances are called saturated instances. The third instance becomes idle, called cached instances. By doing so, we could release resources with a higher sensitivity without evicting instances. Now that the third instance does not process requests, it can be approximated that the third instance is evicted. So such an operation would also update the capacity table, freeing space for other instances, and thus increasing the deployment density. After the releasing phase, if the load re-rises before evicting the instance, we could also use rerouting to let the third instance handling requests again, turning it back from a cached instance to a saturated instance. Such logical cold start can be done in 1 millisecond, avoiding additional cold start of overheads. We also use an on-demand migration mechanism to handle the corner case, where the node has no room for function 1's logical cold start. More details are in the paper. Finally, is the evaluation. Jiagu's goal is to effectively improve resource utilization with low cost. We first evaluate the scheduling cost and found that on 4 real-world traces from Huawei Cloud, Jiagu can reduce about 90% of model inference on critical paths, and thus achieving about 90% lower scheduling cost. If we sum all the code starts costs during the evaluation, we could find that dual-stage scheduling could effectively reduce the number of code starts, and the prediction scheduling can reduce the cost of each code start. So, as shown in the left sub-picture, if the system creates instances with the method cfork, Jiagu can achieve an 80% lower total code start overhead. While overheads are reduced, Jiagu is further able to achieve efficient improvement in resource utilization. Compared to one of the state-of-the-art scheduling systems, GSite, Jiagu is able to increase deployment density by 22% while ensuring the QoS. In conclusion, Jiagu optimizes resource utilization for serverless computing. It introduces pre-decision scheduling and dual-stage scheduling to optimize overcommitment and autoscaling separately, achieving high resource utilization and low cost. Thank you. If you have any questions, I will try to answer them now, or you can contact the authors. Thank you.